The following may include brief excursions into the basics so it can serve the needs of researchers as well as instructors. It is not intended for students presently taking first-year non-major statistics. It attempts to include what should be added to and what should receive less emphasis in the little changed, over half-century-old first-year non-major statistics curriculum. This 1 or 2 course curriculum is the basis upon which tens of thousands of social scientists and STEM scientists structure the manner in which they collect and analyze their data. This curriculum is a critical part of such students' training because, depending on the student's field of study, research typically focuses on data collection and analysis. It is often the only statistical training the majority of these students are presently getting, despite the fact that their career may lead to a focus on random sampling for inferential testing with the intention of publishing. You can pause the video by clicking on the little pair of vertical lines, or you can control its speed by clicking on the little cogwheel as shown. A major challenge in modern research is answering questions about populations such as, do people who engage in intensive sports outlive those who do not? We cannot get data for everyone in such populations, but we can take random samples and then compare them to find the probability that they are meaningfully different. This chancy process is called statistical inference and has justifiably tended to be the focus of non-major training in statistics. It is customary to reject null hypotheses that are unlikely to be true due to chance alone and accept an alternative hypothesis as likely to be true. If the null hypothesis that there is no difference is rejected as being too unlikely, the alternative hypothesis that there is a difference is accepted. Until recently, when many, if not most, statisticians agreed that it should be lowered to 1%, any probability equal to or less than 5% was accepted to be too unlikely to be due to chance, and the null hypothesis was rejected. This implies that not much more than 5% of published research should be non-reproducible. However, there is widespread agreement that over 50% of published research cannot be reproduced. This video suggests how to avoid contributing to this disaster. There is a question of how big a difference can be detected. Most non-major students have come away thinking that inferential testing attempts to detect any difference, no matter how small. Some of them eventually go on to publish research papers that directly or indirectly imply that these tests can detect any difference, no matter how tiny. This confusion could be partly due to the fact that the null hypothesis states that there is no difference. Although verbally confusing, this merely provides a zero difference starting reference point for the numerical computations. Except for tradition, the null hypothesis could have been more conveniently stated as, the reasonable minimum difference is not equaled or exceeded. But do the students even come away knowing that there is such a thing as a reasonable minimum difference, let alone that they can actually take control of it? Then, if the probability of the results having happened by chance alone is less than the chosen cutoff, alpha, either 1% or a reckless 5%, the results are assumed to be meaningless and simply due to chance. In such an instance, the test is not statistically significant, and there is no gain in information from the actual testing procedure. However, it is important that the test occurred. If the researcher finds that the test has attained at least an 80% chance of detecting a reasonable minimum difference, then at least the results, along with the methods and materials, the reasonable minimum difference, and the estimated power to detect, should be published in a journal of non-significant results. The appearance of, and for many, the delusion of testing for absolutely just any difference, no matter how small, has led many researchers to totally denounce all statistical testing. In application, detecting an infinitesimal difference would require an infinitely large random sample. Even nearly infinitesimal differences would be useless and would create confusing hypersensitivity because no two things are perfectly the same anyway. Competent researchers use procedures called power analysis to estimate a sample size that will target what they choose as a reasonable minimum difference. If the researcher does not take control and define the reasonable minimum difference, then the sample size and the variability of the population will choose a minimum difference anyway, and it might not be at all what the researcher expects. Typical sample sizes presently in use tend to be too small and can only detect an unreasonably large difference. The allegedly necessary assumption of normally distributed raw data for parametric testing is often an issue in statistical teaching, not only for training researchers, but even in courses intended for actuaries. Most of the proofs and explanations of parametric procedures shown on YouTube, including classroom lectures at respected institutions, start with the phrase sampling from a normally distributed population. Except for the fact that normality would lead to more rapid convergence to an ideal, the assumption of a normal distribution of the raw data is mathematically unnecessary for formally proving their assertions. If normally distributed raw data were necessary, parametric procedures would be useless. The assumption of normality is misleading because almost normal distributions, such as human heights, are rare, and truly normal distributions of raw sample data are non-existent in application. So the samples I have included here are mostly from two truly random flat distributions, random weather-generated radiostatic and hot bits radioactive decay. After a literature review, the first thing the researcher must do is estimate the sample size. Not to do so would be madness. One could not evaluate either the cost or the practicality of their particular approach to research. A researcher could not know what the reasonable minimum difference was when using an arbitrary sample size. That is, the researcher could not know how big a difference was necessary to be detected. However, published evidence of madness is rampant. Most of the sample sizes used in past publications or in present publications were arbitrarily chosen. Whether appropriate or not, introductory courses tend to emphasize a parametric test by student. Student was anxious to find an inferential test to compare batches of barley, hops, etc. for Guinness Brewery that were arriving in huge quantities from many sources. As you can see in this familiar equation, T is found as the ratio of the difference between two means relative to the variability of the means, the standard error. Student knew that under random sampling, the means and the variance were independent of each other. That is why he correctly chose the t-distribution and not the normal distribution, z, to evaluate this ratio. He knew the t-distribution adjusted for the sample size, but the z-distribution does not adjust for the sample size. So he used t when devising his t-test to examine the question of whether the difference between the means is larger than would be expected by chance alone. Student's t-test was further expanded on by both Student and R.A. Fisher to include what is called a one-sample t-test, in which one of the means is simply a hypothetical value, often 0, as when you are testing pairs as though they were single samples. Student's t-test would have been a universally applicable test if all the data were normally distributed. However, as was pointed out by both Carl Pearson and R.A. Fisher, normally distributed data is never found in application. Nevertheless, the theoretical requirements of the t-test are assisted by the central limit theorem, which comes to the rescue by guaranteeing that as the sample size grows larger, the t-distribution of the means approaches the normal, z, distribution. However, due to a lack of power at small sample sizes, students' t-test rarely works for samples under 30. Therefore, it is not a small sample test. The effect of sample size is partly demonstrated here by the graphs from my massive examination of random electromagnetic disturbances and radiostatic caused by weather phenomena. The raw random samples produce a flat distribution with some hair due to variability. Sample sizes of at least 30 tend to produce distributions of means that at least approximate the t-distribution, which ultimately converges to normal as per the central limit theorem. The tendency for the means to approach looking like a normal distribution when graphed with sample sizes of 30 or more might be why the supposedly magic number 30 is so commonly used in statistics. Many texts call samples of 30 large, but samples of 30 still cannot handle skew very well, so they can be biased, favoring one outcome and opposing the other. In the extreme situation above, this is visible as differences in the areas of tails on one side of the mean of the means versus the other. In agreement with the literature, sample sizes of 80 tend to produce a distribution of the means that is a slightly better approximation of the t-distribution for skewed data. An example of a conveniently mound-shaped, nearly symmetrical distribution is the BRFSS, self-reported random telephone interview height data. Samples of 30 or so tend to bring such distributions rather close to normal. Unfortunately, even samples of 30 rarely have enough sensitivity, also called power, to dependably detect an elephant in a living room. In almost all situations, it is a misnomer to say student's t-test is a small sample test, but if you can properly estimate the suitable sample size to attain the power to detect what you choose as a reasonable minimum difference at least 80% of the time, meaning 4 times out of 5, the CLT will almost always provide for meeting the theoretical requirements of student's t-test. You can, and perhaps should, seek a power of 90%, meaning 9 times out of 10, but that would require a much larger sample size. So the crucial requirement before starting data collection for any inferential test is to carefully estimate the sample size required to detect if a reasonable minimum difference exists or is exceeded. Starting without a properly estimated sample size is undoubtedly a major part of why the literature is plagued with unreproducible results. Jacob Cohen was a pioneer in attempting to determine the correct sample size for students' t-test. He defined an effect size estimator called Cohen's d, along with a set of small, medium, and large sample sizes corresponding to values of his d. Perhaps Cohen was uncomfortable with trying to get a sufficiently accurate estimate of the variance, s squared. In his formula for d, he mysteriously included the unknown and unknowable exact standard deviation, sigma, instead of the standard deviation estimate, s, which is the square root of the variance estimate. Subsequent authors have presented versions of d under various names. These versions use S, implying a pooled estimator, in an endeavor to make some sense of Cohen's d. Then on page 25 of his 1969 edition of his book, Cohen backed away from his sample sizes for small, medium, and large, explaining that they were merely situational rules only for, I quote, the specific content and research method being employed in any given investigation. Despite the fact that even situationally adjusted values of small, medium, and large are impractical in application, they and even the original sample sizes for small, medium, and large unfortunately still commonly appear in psychological and educational research papers, as well as being misleadingly recommended on the Internet. Using Cohen's d for sample size estimation has surely led many researchers to failure, or at least slowed the progress of their research. Students must be warned not to use it for estimating sample size. An often acceptable approach to sample size estimation is the increasingly popular and seemingly reasonable z-based estimation equation above, where z refers to the cumulative normal distribution. However, the means of random samples tend to be t-distributed and only eventually converge to a z-distribution. Z-based sample size estimation underestimates by almost 22% when a sample size estimate n should be around 15, and by almost 10% when the estimate should be around 30. The underestimation decreases as the sample size for the variance increases, but it is still underestimating at more useful sample sizes, and it might still be 2 samples too small when the sample size should be as large as 100. So, in actual statistical application, sample size estimation based on a z-based variance estimate is not close enough for required sample sizes below about 150, although knowing the mean for either corrected or uncorrected sample size estimation is not required. A sufficiently accurate variance estimate is required. Assume I am an engineer who wishes to compare a new antenna to see if it can detect 20% more static than can the antenna used by random org. A huge sample of 100 million radiostatic samples from random org had a mean of about 21.4764 and a variance around 153.7. In this case, I choose a minimum d of about 4.2953, meaning 20% of the mean. So, I look up the appropriate values of z and fill in all the values with squaring where required. 20% of a mean will often, as in this instance, be a rather large and therefore easy to detect reasonable minimum difference, so the resulting estimate is only a moderate 84 samples. However, recall that less than 150 samples is not a large enough estimate to be used without adjusting for the more correct t-distribution of the means. So I use the z-based estimate of n to estimate the degrees of freedom for the initial two values of t. Then I substitute those values of t in place of the z values in the estimation equation and iterate, meaning I repeat the calculation using each succeeding estimate to get a new degree of freedom estimate to plug in a new value of t, as shown above. This recursion will finish quickly after the initial z-based estimate. The quick finish is because I am seeking a counting number, the sample size. That is, when I reach an estimate value that cannot be rounded to a different integer from the preceding estimate of the sample size, the iteration must stop. Then I round up to the nearest counting integer as the final sample size estimate, in this case 87. This simple recursive algorithm is easily adapted for one sample t-test, two sample t-test, paired t-test, etc. Sounds wonderful. Hardly any difficulty at all. What could go wrong?
Hold on there. We still do not know enough to run such an estimation equation. Where can we get a standard deviation to fill in as s?
Well, that is both a challenge and an opportunity for improvement.
The true variance, commonly denoted sigma squared, is unknown and unknowable. Whether you are choosing sample sizes for students' t-test or for a confidence interval, all of the approaches to sample size estimation mentioned so far, my own adjustment included, require a sufficiently accurate estimate, s squared, of the variance, which is denoted as sigma squared. Note that such a sample size estimate is linearly dependent on the variance estimate. If the variance estimate is twice as much, the sample size estimate doubles. As many programmers are becoming aware, estimating the variance for, say, estimating sample sizes is not a trivial undertaking in the sense of just taking small samples. Comments and questions regarding the difficulty of estimating the true variance even turn up on Stack Exchange. The various participants claim that they seem to need thousands of samples just to estimate a variance within a 10% accuracy. In all useful approaches to sample size estimation for the t-test, the estimate of the size of the required sample is proportional to the variance s squared that is being used. If an estimate of the variance is accurate to only within 10%, a test that only needs a sample size of, say, 250 could be overestimated by as much as 25 samples or, more harmfully, underestimated by as much as 25 samples. In application, finding the appropriate sample size for a parametric test like students' t-test would demand a very accurate estimate of the variance in order to attain a sufficiently accurate sample size. The required a priori random data for estimating the variance would be disqualified from being used again and would have to be discarded before collecting the data for the test itself. If you do not already have a huge amount of pre-existing data, estimating the variance would require collecting and then discarding hundreds or even over 1,000 a priori random samples before getting on with your research. Could the classical curriculum for non-major statistics courses need drastic changes? Is there a desperate need for revision? Could the curriculum that I and most others have been teaching for decades be implicated in the present research publication problem in which a large proportion, if not a majority, of published results cannot be duplicated? I have withdrawn the first edition of my book for revision. It updated the classical curriculum from a survey of the latest literature up until 2022. And it also encouraged sample size estimation, but among other difficulties, it quoted literature that incorrectly said that an a priori, meaning before the fact, sample size of 25 to 30 would be adequate for variance estimates to be used in estimating parametric sample sizes. I ran simulations using various huge data sets to seek answers and solutions to these challenges. These simulations confirmed that using less than very large samples for variance estimation was very wrong. This tends to limit parametric tests to where historical accumulated data handily provides for precisely duplicating the manner in which it was collected and also is massive enough for sufficiently accurate variance estimation. Here is a quick rundown on some simulations I have been running on an unnecessarily overpowered custom workstation using samples of tens of thousands to millions using pandas, mostly at NP float 128 in order to minimize rounding errors. I used a commonly applied calculation of the variance, meaning the above formula that is generally presented to define the variance. With a little patience, skeptics should be able to run similar simulations on data in their own fields using any handy computer language, even on a high-quality laptop if it has sufficient storage capacity. Above is a graph of individual point estimates of the variance S-squared, starting with a sample of 3 and increasing by 1 sample at a time. As you can see, samples of size 3 through 500 produce alarmingly chaotic results that vary drastically each run. The chaos tends to decrease, but at a decreasing rate as the sample size increases, as seen when these graphs are extended out to 6002. Repeated repetitions of this exercise produce similar graphs that tend to confirm that the sample size estimates for students T would range from about 769 up to many thousands of a priori sample values, even if the test itself happened to require only a moderate sample size. For a different visualization, the above graph includes 30 points for each sample size to present a more generalized view of why it is costly in terms of a priori samples to estimate the sample size for a student's t-test. The above estimation equation involves an approximation of the chi-square distribution of the variance to seek the size required to get an estimate that is within a given percent, rho, of the true variance. The quality of this approximation is assisted by the CLT so that the chi-square distribution of the variance approaches acceptably close to the normal distribution above an a priori sample size of about 89. Although this sample size of 89 meets the theoretical distribution requirements for estimating parametric sample sizes, a sample of 89 would only get your estimate into a rarely useful, very wide range of possible variance estimates. No matter how you approach it, the very high cost in terms of a priori sample size to obtain an estimate S-squared and, by taking its square root, S, of the standard deviation sigma persists. The Greek letter rho refers to what you accept as the minimally acceptable percentage of over or underestimation of the variance, the value that might be referred to by the words nearness or within. Note that the sample size estimates vary directly with the variance estimates, so rho refers to how close you want your sample size estimate to be. Alpha is the maximum chance you wish to take of overestimating the variance for that particular value of rho. Assume you only seek to be likely to get within 10% of an accurate estimation of the variance and that you are willing to accept a 95% chance of not over or undershooting that range. The resulting sample size estimate at alpha equal to 5% or for a 95% CI of the variance equals 769. Note that this whole sample of 769 values will have to be discarded before sampling for the real t-test. Also note that the accuracy of the variance estimate, especially if it underestimates, will affect the power of your t-test. More realistically, the cost of getting within 5% of the true variance would necessitate collecting and disposing of 3,075 a priori sample values. So students' t-test and its derivatives can be very useful for continuous data if and only if you make a sufficiently accurate before the fact estimate of the variance and you can precisely duplicate the manner in which it was obtained. One of its developers, the brilliant pioneer statistician R.A. Fisher, eventually insisted that students T was only suitable for quality control. We should not limit it that much, as it has potential in areas such as political science and public health. Huge public health medical databases might provide exactly what you need for estimating sample size. However, the manner in which the data was collected may vary from place to place and also in time. The popular blood pressure cuff design has changed in the last decade or so, and there are starting to be crucial changes in the timing of when, after the patient arrives, that the measurement is taken. Your research conditions and procedures must duplicate the conditions by which the data upon which you based your sample size estimate was obtained. Special attention must be paid to the interpretation and correct handling of data that has been weighted to reflect population differences such as age and medical history. Regardless of the country and motive, government data is often weighted in various ways to make it more understandable to laypersons or to justify policy. Researchers must carefully investigate and seek answers before deciding if they can understand and adequately duplicate the conditions under which the available data was collected, cleaned, weighted, and reported before using a sample size estimate from someone else's historical data. The information covered so far mostly regarded continuous distributions. However, counts are not continuous, and assuming they are the number of things, har, counted as of interest among all the n things being considered, the result can be seen as r pluses contrasted with n minus r minuses. That is, assuming randomness, the number of customers, r, that buy chocolate at the grocery store can be divided by its hopefully large enough sample size n to estimate a probability p, or they can be scored as plus for buying versus minus for not buying. Note that with random sampling, p estimates a proportion of customers that buy as well as the probability that they will buy. Almost any kind of randomly obtained data can be handled similarly by counting each outcome of interest as a plus, as opposed to a minus, or 1 as opposed to a 0. This suggests that testing based on the binomial distribution might be a good initial introduction to testing in our non-major introductory classes. Although direct estimation of binomial probabilities from the binomial theorem is tedious for barely large samples and can be a challenge even for computers when samples are adequately large, the above approximation equation facilitates binomial testing with large samples. It takes advantage of the fact that random estimates of probability via the proportion p = r divided by n can be treated as a mean and, under the central limit theorem, randomly drawn proportions become normally distributed as the sample size becomes sufficiently large. This facilitates a variety of binomial testing approaches, including scores from counting either paired or unpaired results, where n can be either the number of pairs or the overall sample size, respectively. It might be the best introduction to testing in an introductory course as it relates to the CLT and the law of large numbers and provides a basis for better understanding and applying the sometimes slightly more powerful order-based non-parametric tests. This z-based normal approximation of the binomial distribution is often a great testing strategy, especially if a power estimate-based sample size can be used via a hypothesis that p = 1/2, which is equivalent to a hypothesis that the number of each class of interest is the same. Hypothesis-based values of p can be used for the binomial approximation if they are close to p = 1/2, meaning there is no difference. At p = 1/2, the binomial distribution becomes increasingly symmetrical and mound-shaped as the sample size grows larger. However, moving away from p = 1/2 quickly moves the distribution towards an increasing amount of skew. This skew becomes extreme below p = 0.3 or above p = 0.7, in other words, 30% or 70%. Above is an equation for finding the required sample size for a simple binomial approximation-based test. As you can see, it can be used for different maximum probabilities of false significance, alpha, and different powers, 1 minus beta, as well as different hypothetical values of your chosen reasonable difference as a difference from p. If you are using the binomial approximation with a total population of a limited and known size, uppercase N, the sample may have to be a little larger than your initial estimate. That is, you should then adjust your initial estimation of the sample size for the binomial approximation using the above equation. This is useful for sampling from a single organization or school. There are variations of the binomial approximation equations that contain a correction for continuity, meaning for smoothing the stair-step effect of the discrete values in the true binomial distribution to make it be more like a normal curve. However, a continuity correction rarely has a meaningful effect when the sample size is large enough to have a useful power. Sample size estimation for the binomial approximation does not require previous data to be available. Some sample size estimates for the hypothesis that there is no difference are shown here for alpha equals 1% and beta equals 20%. To have a reasonable minimum difference of, say, d-min equal to 5% might be a bit large to be called reasonable in some applications. When using a low-risk alpha of 1% and a reasonable minimum difference of 5%, meaning 1 in 20, the sample for a two-tailed sign test for, say, a master's degree program with alpha equal to 1% and beta equal 20% would require a sample size of n equals 1,168 pairs. However, one-tailed tests cost less, and for a one-way, meaning one-tailed test, it would need a less costly sample size of 705. Even if the researcher wished to chance a risky alpha equal 5%, a two-tailed test would still require a sample size of 1004. Regardless of the reasonable minimum difference and one or two tails, students and researchers should not be misled to believe that small sample inferential testing is practical for original research. Even yes, no sampling in common applications such as opinion surveys generally requires sampling over 1,000, often thousands, of participants or respondents. Different questions in different settings may require different approaches, and for a great many questions there may be more efficient tests than a binomial-based test. Then there is the problem of who you are really surveying. How the researcher samples defines the population. Surveying in the street gives you one population. Surveying by mail gives another, and surveying by phone defines its own population. As for all statistical testing, designing the actual sampling procedure is a major challenge that requires thought as well as calculation. The binomial approximation might be classed as either parametric or non-parametric. Although the binomial approximation is not quite as powerful as the order-based non-parametric tests, it can be especially useful because it can be adapted to construct confidence intervals for proportions such as percentages using z rather than t. The more widely applicable order-based non-parametric approaches examine the probability that sequences of values will fall into some non-random order. The parameters of ordered data are well known, so it is not necessary to know the variance of the raw data to estimate sample sizes for such tests. Like the binomial approximation, the order-based non-parametric procedures do not require the raw data to be normally distributed. Literature criticizing the order-based non-parametric test says that if you actually get an adequate estimate of sample size for a student's t-test, an equivalent non-parametric test would require between 3% and 7% more samples to be as powerful as a t-test, but that is extremely misleading. The way to estimate the sample size for an order-based non-parametric test relies on the well-known parameters of any random data that can be ordered. For any given alpha, beta, and the reasonable minimum difference, d-min, the sample size is the same for an order-based non-parametric test regardless of the distribution of the raw data. However, the sample size for parametric tests such as the t-test also depends on the variance, and depending on the raw data, it can either be larger or smaller than for a non-parametric test. In any case, such criticism overlooks the enormous cost in terms of throwaway samples needed for parametric sample size estimation. For most original research, this cost makes properly planning sampling strategies for parametric tests impractical except for situations in which there is a massive pre-existing source of reproducible data. But because most non-parametric tests require no sacrifice of data to estimate sample size, such tests are wonderful because you only need to decide on an alpha, a beta, and a reasonable minimum difference to make a sample size estimate. What is less wonderful is that order-based non-parametric tests are not about the difference between the means and therefore cannot contribute to confidence interval estimation. The interpretation of these non-parametric results is also different because the usually most practical order-based non-parametric tests look for stochastic inequality. That means they test whether there is a greater probability that if you randomly draw a single item from one population, you are more likely to get a higher value than from the other population. That is, you might be more likely to find a great future quarterback in one city than in another. They are not about whether a central measure is different. They do not even say, as is commonly believed, that the medians are different. There actually exist situations in which there is a real difference that can be detected by non-parametric tests when the population medians are the same. Here is a quick look at a non-parametric test that should be very often used instead of students' two-sample t-test. It does not require pre-existing knowledge about the variance of the raw data, and it is often more powerful than a t-test if skew is present. The Wilcoxon's two-sample sum rank test, which is extended by drawing from the Mann-Whitney U-test, is a non-parametric counterpart of students' two-sample t-test. It is based on ordinal position, meaning rank as in lists or queues. Conceptually, the workings of the Wilcoxon test are as though you took each score from population A and compared it to every score in population B, one signed test at a time. If most of the time the scores of population A are higher, that would indicate a higher probability of randomly drawing what is called a superior outcome from population A. Under skewed conditions, the Wilcoxon summed rank test is reported to be 3 to 4 times more powerful than a student's t-test. Some authors report that students' t-test is better when the variability of the data is meaningfully different. However, that would still leave the cost in terms of the a priori samples of estimating a sample size for students' t-test. A downside of otherwise suitable order-based non-parametric tests is that when ordering the data, each tie reduces the power a little. This means that you should always use a little larger sample than your sample size estimate using the otherwise easy non-parametric estimation formulas. Unfortunately, it is impossible to be a priori certain how much slightly larger your sample should be without prior experience with the type of raw data being sampled. 5% larger might be prudent. It would be unlikely to produce hypersensitivity, meaning it would not become extremely sensitive to tiny environmental effects. To use the Wilcoxon's two-sample sum rank test for equal sample sizes, the researcher ranks all the test scores together from 1 to the combined number of samples n, A and B, either from the smallest to the largest or from the largest to the smallest. However, for unequal sample sizes, they must be ranked once for one way and once for the other. After ordering the combined data, you must separate the rank scores into their corresponding treatment categories. Then you sum all the ranks, and the smallest sum is WR. The size of that treatment sample is NR. For sample size estimation, you need to choose the maximum allowable probability of false significance, alpha, and then the power, 1 minus beta, to detect the exact outcome that you are looking for, where beta is the probability of not detecting your chosen reasonable difference. The research community used to insist that alpha should be no more than 5 pers, but many modern statisticians agree that alpha should be no more than 1%. They have realized that it is unreasonable to declare that something is scientific truth or that we should change our legal, educational, or social behavior or structure when there is still a 5%, meaning a 1 in 20 chance of having gotten false significance. The power, 1 minus beta, is customarily 80%, however 90% would be better for order-based tests if you can afford the cost of additional samples. For information on how to use the Wilcoxon testing approach with Siegel-Tukey ranking to test for differences in variance, or for a one-sample test, you should refer to a suitable text, or perhaps you can find the material you need on the internet. Incidentally, the normal z-distribution often appears even in non-parametric tests like Wilcoxon's test for mathematical reasons, and does not assume that the raw data is normally distributed in such situations. This use of z is because the sums of random data, even random samples of ordinal positions, tend to behave like means, and as the sample size grows larger, their distribution converges to normal analogous to the central limit theorem. Because the z distribution is symmetrical, the absolute value of z for beta equals 20% equals the absolute value of z for beta equals 80%. This results in the same outcome no matter how an equation using either of the absolute z values for beta or for 1 minus beta appears in a particular text or website. Sample size estimation for Wilcoxon's test requires you to choose the total chance of a superior outcome, PS-min, that you minimally wish to detect. Under the null hypothesis of no difference, meaning a 50-50 chance of a superior outcome, an item drawn at random from either population has a probability, P, equal to 50% of being superior. So PS-min equals the reasonable minimum difference, D-min plus 50%. Be cautious about this. Some sources seem to use PS-min in place of D-min. C is an adjustment for when the sample sizes are not equal. It defaults to 1/2 with equal sample sizes. If one sample size is limited, you should be able to do some scratch calculations and iterate to create an acceptable value of C. A superior outcome is not necessarily superior in the way you may think. Superior may be a greater probability of getting the flu, the reason for referring to PS. Min et al. Is to emphasize Wilcoxon's original idea of testing to find the population for which the next individual sampled is more likely to meet the criterion being sought. Inferential processes are rather dependent on the question you seek to answer and the viewpoint from which you phrase it when you ask. The Wilcoxon test does not specifically refer to the popular central measures such as the mean and median. It represents a more dynamic point of view. It focuses on the proportions of the expected qualities of randomly sampled individuals. Thus, there is a greater likelihood of a male than of a female being a recidivist. There seem to be as many different variants of Wilcoxon's test as of students' t-test, and they seem to be relatively interchangeable if you can control the power through selecting a proper sample size. Despite order-based non-parametric tests not providing for associated post-hoc confidence intervals, there are still a lot of informative descriptive statistics that are appropriate if any valid test is statistically significant. These include effect sizes and graphics such as box plots and violin plots. Suppose you need to know the sample size that is necessary to have an 80% power to detect if there is a PS-min equals 60% or greater probability that the next patient will lose more weight with medication A than with medication B, with no more than an alpha equal to a 1% chance of false significance. As for all inferential tests, the greater the difference, the greater the chance of detection. This estimate specifically refers to a one-way test for equal to or greater than a 10% reasonable minimum difference. But the detection rate will increase rapidly if the true difference above 60% is higher than your chosen 10%. That is, the true power is higher if the true unknown difference is greater. Therefore, an 80% detection rate, which equates to detecting a minimum of 4 out of 5, is stronger than it may seem. The answer is n equals 251 for each sample. It was found without having to estimate the variance. So it applies to all equal sample size one-way Wilcoxon tests that seek beta equal to 20%, alpha equal to 1%, and D-min equal to 10%. It is advisable to provide a safety factor of about 5% more items per sample for ties, in this case for a final n equal to about 264. You may modify this safety factor as you become familiar with the specific sampling design and the overall population being examined. Using 1 minus beta for a power equal to 90% would both be more sensitive and would further reduce the chance of post-hoc power turning out to be less than even 80% when the number of ties is awkwardly high. Recall that you can and should always report tests that fail to get statistical significance when the post-hoc power was at least an 80% probability of finding a reasonable minimum difference that is clearly reasonable. All this percent stuff might be a bit confusing when starting the experimental design. However, the answer is often very clear, as when you can tell a physician that the evidence predicts an increased chance of a weight loss for the next patient to be prescribed medication, A, as opposed to the original medication, B. So, in the absence of extreme skew, students' t-test and its derivatives, such as the ANOVA, along with t-based confidence intervals, might be more informative than order-based non-parametric tests. But they are only practical when you have a sufficient amount of pre-existing data to estimate a sufficiently accurate variance for sample size estimation. This means their use should be limited to rather specialized situations. However, all statistical testing deals with chance and is always chancy. We will never be perfectly certain using statistical test outcomes because the only reason for using statistical inference is that we cannot examine the whole population being considered. The student's training must especially emphasize that testing without a sample size estimate is a pitfall for careless researchers. Without a power analysis, they cannot choose how huge or tiny a difference is being sought, nor can they control the chance of detecting it. They should also know that testing for zero difference is impossible for any statistical test. Likewise, they must understand that just grabbing a sample of any handy size may result in the test being too weak to detect much of anything. The folks who did so were often unaware that they were sacrificing control of the size of the targeted minimum difference and of the power to detect it. Occasionally, the researcher has no choice of a sample size and must take what is available. Of course, even then, if statistical significance happens to be found, it would be likely to be meaningful. But without statistical significance, the researcher would not be justified in even publishing in a journal of non-significant results unless a post hoc, meaning after the fact, power analysis showed that there was an 80% chance of detecting a reasonable minimum difference that was at least reasonable. Otherwise, it would be meaningless to report that a powerless, non-significant statistical test occurred. However, even if the researcher cannot control the sample size, the researcher can be warned in advance if a particular experiment or survey is practical by estimating what sample size would be needed to obtain a reasonable power. So, an a priori power analysis can greatly reduce the probability of useless financial waste and disappointing results when choosing the focus for, say, a thesis or dissertation, or for deciding whether to make a business investment. Many researchers see statistical tests such as the student's t-test as simply ritual, or they may see statistical tests as revealing absolute certainty. When, as is so often the case, we cannot test, interview, or measure every member of the population, statistical tests only produce evidence of a probability of something, and probability implies its opposite, uncertainty. Due to chance, statistical tests can, and sometimes do, fail to reject your null hypothesis when it is false. Because of the uncertainty involved in the testing and the data collection process, using statistical inference to attempt to generate discoveries by just testing without any justification will often mislead the researcher, R.A. Fisher felt that statistical tests should be used to challenge your conclusions rather than confirm them. Maybe this viewpoint should be reconsidered by the research community. In any case, when a researcher has sufficiently mastered a subject, questions based on their expertise are very likely to arise. Then, the researcher needs sufficient reason to use a chancy test for a consequential plausible idea or a consequential possibly erroneous idea. A healthy attitude from the Bayesian School of Statistics is that we are seeking evidence to adjust our degree of belief. We definitely need changes in our non-major curriculum to encourage the use of tests and procedures most commonly used by the most students. Therefore, we must turn our focus away from students' t-test and its derivatives, and we must also increase the focus on power analysis, especially power analysis for sample size estimation. Without a community-wide agreement on these curriculum changes, our students will encounter difficulties when transferring to other institutions, and perhaps even with graduate advisors, some of whom have an almost dogmatic belief in the traditional parametric approaches for any and every research project. So we come to the end of this video, and as it suggests, the academic community has a wonderful opportunity to update the teaching and application of inferential statistics. Because of the decades-long lag in updating the curriculum generally used for training non-major statistics students, we now have a sizable variety of possible improvements, which together may lead to a new era of research productivity and success. Meanwhile, researchers who are already aware of facts such as those presented here will have an increased probability of a productive and successful career.